in this problem, we're essentially going to calculate the frequency of a standing wave. So if two successive harmonics of a vibrating chord are 240 Hz and 320 Hz, find the frequency of the first harmonic. So we're looking for the fundamental frequency of our chord. So before we begin our calculation, let's recall the following two important formulas that we'll need to use in this problem. So formula number one essentially states that the product of the wavelength and the frequency of our wave is equal to the velocity. And equation number two gives us a relationship between the wavelength, between the harmonic and our length of our chord. So it tells us that the length of our chord L is equal to the product of the harmonic number n multiplied by the wavelength at that harmonic, lambda n, divided by 2. So we're going to use these equations in just a moment. But first, let's look at our information. So we want to calculate what our frequency is when n is equal to 1, when our harmonic is 1. Now, we don't know what the harmonic number is at 240, and we don't know what the harmonic number is at 320. But we do know that whatever this harmonic is, this is 1 plus, because we're looking at successive harmonics. So let's suppose this corresponds to harmonic n, then that means this must correspond to harmonic n plus 1. So at harmonic n, our frequency Fn is equal to 240 Hz, and at harmonic n plus 1, our frequency is equal to Fn plus 1 is equal to 320 Hz. Now, notice that when our frequency is 240 and when our frequency is 320, in both cases, we're using the same exact chord. And because we're using the same exact chord and the velocity depends on the type of chord we're using, because we assume our tension and mass per unit length is the same in both cases, that means our velocity is also the same. So the velocity when we're at the nth harmonic and the velocity when we're at the n plus 1 harmonic is exactly the same. So velocity remains constant regardless of our frequency. That basically means if the frequency increases, the lambda must decrease. So we get the following result. The velocity at the nth harmonic is equal to the velocity at the n plus 1 harmonic. Now, Vn is simply equal to the product of lambda n and Fn, and that's equal to the product of lambda n plus 1 multiplied by the frequency n plus 1. Now, we know what our frequency n is. It's 240, so we have 240 is equal to lambda n, and we also know that our frequency n plus 1 is 320. So this is equal to 320 multiplied by lambda n plus 1. So let's now take the ratio of lambda n to or divided by lambda n plus 1, and we get 320 divided by 240, and that simplifies to 4 divided by 3. So we see the ratio of the wavelength at the nth harmonic to the wavelength at the next successive harmonic is equal to 4 divided by 3. So we're going to use this fraction in part 2 of our problem. So let's look at part 2 where we're going to apply this equation. So not only is the frequency not only is the velocity constant in our chord, our length is also constant. So that means the length at any given point is exactly the same. The length at any given harmonic is exactly the same. So the length of our chord at the nth harmonic is equal to the length of our chord at the n plus 1 harmonic. So Ln is simply, well, it's n multiplied by lambda n divided by 2. And this is equal to Ln plus 1. So n plus 1 multiplied by lambda n plus 1 divided by 2. So notice our 2's cancel and we're left with the following ratio. So we essentially want to find this ratio. So lambda n divided by lambda n plus 1 is equal to n plus 1 divided by n. So we know that this ratio found in part 1 is 4 divided by 3. So n divided, or n plus 1 divided by n is 4 divided by 3. Now we can cross multiply and solve for n, and we see that n is equal to 3. So, what we essentially did in part 1 was we found the ratio of the two wavelengths. And then in part 2, we used that ratio to calculate what the actual value of n is. So that means this is our third harmonic and this is our fourth harmonic. Because if n is equal to 3, then n plus 1 is simply 3 plus 1. So this is the fourth harmonic. So now we want to use this information to calculate what the frequency is at n minus 2, or what the frequency is at our first harmonic. So we're going to use this result once again. We're going to use the fact that the length of the chord at any given harmonic is exactly the same. So the length of our chord at the first harmonic, n minus 2, is equal to the length of the chord at the nth harmonic, or the third harmonic. So this is equal to this. Now this is equal to, well, it's simply n minus 2 is equal to lambda, or n minus 2 multiplied by lambda n minus 2 divided by 2. And this is simply n multiplied by lambda n divided by 2. Once again, the 2's cancel, and now we know that 3, or n, is equal to 3. So we have 3 minus 2, which is 1, and n is simply 3. So we have lambda n minus 2, our wavelength at the first harmonic, is equal to 3 times the wavelength at the third harmonic, or at the nth harmonic. We simply replace n with 3. So now we see that 1/3 is equal to the ratio of our wavelength at the nth harmonic, at the third harmonic, to the ratio at the first harmonic. And finally, we use this equation once more. So not only is the length the same at every harmonic, the velocity is also the same. So our Vn minus 2 is equal to Vn, which simply means the velocity at any harmonic is constant. So we replace this with simply the product of the wavelength at that harmonic multiplied by the frequency at that harmonic is equal to the product of the frequency and the wavelength at that particular harmonic. So once again, we have to solve for our Fn minus 2, and we get that Fn minus 2 is equal to lambda n divided by lambda n minus 2 multiplied by Fn. Now our n is simply 3, and we know that F3 is simply, well, it's 240 hertz. And we know that this ratio found here is 1/3. So 1/3 multiplied by 240 hertz gives us 80 hertz. So that is our fundamental frequency, also known as the first harmonic of this particular chord. It's 80 hertz. And notice all we needed to find that was the two frequencies of any two successive harmonics.